This is from the Keno Donnell lab at the University of Bristol. And the talk is about dynamical principles of synaptic receptor sharing across spines in a dendritic branch. The
Yep.
floor is yours.
Can you hear me?
Yes,
Yeah.
yes.
Thank you so much, Olivia. So what I'm looking for are what are the factors and how do they control the count of the synaptic receptors amongst the dendritic spines. So if you take a CA3 pyramidal neuron and zoom into a short stretch of its dendrite, you will see these granular projections, protrusions along the main shaft. And if you further zoom in, you can see the individual spines. Now, a single spine has a spine head and a spine neck, and the top section of the spine head's membrane, there is a dense raft of specialized proteins called postsynaptic density. The Ampa receptors are distributed all over the membrane, but they are present in this small region of postsynaptic density at a very high density. And this is due to the retarded diffusion of the Ampa receptors in the PST due to local macromolecular crowding, as well as the binding of the receptors with the PST95 slot proteins. Now, the importance of the count of these AMPA receptors in the PST is due to the fact that these receptors are closely juxtaposed to the active zone of presynaptic active zone of glutamate release, and thus predominantly shape the amplitude and kinetics of the excitatory postsynaptic potential. So the freely diffusing as well as the PST95 bound receptors in the postsynaptic density are together called by a spatial name synaptic AMPA receptors, and the other receptors are considered extrasynaptic. Now, what are the factors which control the count of the synaptic AMPA receptors at a single spine and the distribution amongst dendritic spines have interested the neuroscience community for a long time. And a lot of studies has actually focused on single spine. Only very few studies, some in recent years, have actually tried to look at how the factors shape the distribution of receptors amongst the spines. Now, of course, there is a well-recognized immense molecular machinery for AMPA receptor trafficking, which shapes the unique distribution profile of the receptors on the dendritic arbor of the neuron. However, it doesn't work in isolation. One of the most prominent input is the presynaptic activity. However, the firing of the postsynaptic neuron also provides input to the molecular machinery through, for example, backpropagating action potential, as well as the local electrophysiological activities in the dendritic branches also provides input to the molecular machinery through, for instance, the dendritic spikes. So a straightforward approach would be to first study the machinery and then study the response of the machinery to the input. So the entire molecular machinery for AMPA receptor trafficking can, for easiness, can be divided into three principal mechanisms. One is the simple membrane receptor diffusion, where the receptors exhibit 2D Brownian diffusion in the phospholipid membrane with a diffusion coefficient of 0.1 micron meter squared per second. But with a 1/10th reduced diffusion coefficient in PST due to local macromolecular crowding, as I mentioned before. And this receptor diffusion causes exchange of receptors between the somatic membrane and the dendrite, parent dendrites and the daughter branches, and eventually between the spine head compartments. The other very important mechanism of AMPA receptor trafficking is the exocytosis and endocytosis, where there is a constant exchange of receptors between the membrane and the intracellular receptor pool. And this happens in the spine head as well as the dendritic shaft. And the intracellular receptor pool is constantly affected by the local AMPA receptor synthesis as well as degradation, and the anterograde and retrograde vesicular transport of Ampa receptors. So this leads to the third important mechanism, which is the motor protein assisted active vesicular transporter proteins, Ampa receptor proteins, where the large cargo vesicles carrying these Ampa receptors move in through anterograde transport into the daughter branch, and the receptors from the intracellular pool are transported back to the somatic compartment, loaded on these cargo vesicles, again walking on the microtubules through the parenchyma. So if one tries to think about an integrated biophysically detailed model for understanding how these three mechanisms shape the count of synaptic Ampa receptors, it becomes very daunting. Now, the point is that each mechanism is regulated by thousands and thousands of proteins and signaling factors, and many of them are undergoing nonlinear computations. For instance, the simplest, even if I look at the receptor diffusion, then the receptor diffusion is very much affected by the size of the intracellular C-terminal domain of different Ampa receptor complexes, the phosphorylation status of the terminal domain, C-terminal domain, and the association of the Ampa receptors with tau proteins such as stargazing. So thinking about an integrated detailed model is indeed daunting, as well as also limited from the point of parameter estimations, because many of the details we still don't know from the experimental point of view. And if suppose someone even comes up with this model sometime, some years later, then this will of course prove to be extraordinarily computationally expensive, and it will be difficult to actually develop a mechanistic understanding. So this necessitates a coarse grain rate mass model. And here I consider a compartment-based reaction diffusion approach, where what I do is that I take a daughter branch coming out from a parent dendrite, and I chop it like a carrot into small compartments. And each small dendritic compartment, the density of the receptors in the membrane of that compartment is shown as R subscript dent, and the intracellular receptor pool in that small compartment is clubbed together, and there is a crosstalk between the membrane and the intracellular receptor pool through endocytosis and exocytosis. Now, the intracellular receptor pools are also constantly enriched with new receptors through anterograde transport, as well as depleted by the retrograde transport. And the anterograde and retrograde transports are independent for each compartments. Now, some of the dendritic compartments also bear spines connected through the spine neck, where the density of the receptors in the neck are shown as R subscript neck, and the density of the receptors in the extrasynaptic membrane shown as R subscript ESN. Now, the spine head also contains an intracellular receptor pool defined as IR spine, which shows a similar mechanism of endocytosis, exocytosis, retrograde, and anterograde mechanisms. And the pool of the receptors in the postsynaptic density are divided into two pools, subpools. One are the free receptor pool and one the bound receptor pools, where there is an exchange between these two pools based on the density of the PSD95 slot proteins, binding and unbinding parameters. So this coarse grain model actually provides a very simple mechanical structure capturing the most essential interactions for trafficking and binding processes. Now, this model works on the system of mostly linear ODEs, where the only nonlinear reaction terms are for the binding of the receptor with the PSD95, and this is just because the binding depends on the availability of the free PSD95 slot proteins. And this model actually works on the list of on these parameters, where there are geometric parameters which define the shape and size of the compartments. Then we define a boundary condition at the initial starting point of the daughter branch, where we are considering a steady concentration boundary condition. And then we have hopping factors, which define the exchange of the receptors between the different compartments through Ampa receptor diffusion in the membrane. And then we have intracellular receptor trafficking parameters, where we have anterograde and retrograde parameters for all the spine heads and dendritic compartments. We also have membrane receptor trafficking parameters, where we have parameters for the exocytosis and endocytosis, and for all the spine head and dendritic compartments. And then we have PST95 density, binding, and unbinding parameters for every PST compartment in the spine. Now, if we consider the dendritic branch as a system, then the anterograde parameters and the boundary condition actually causes influx of receptors into the system, and the retrograde ones actually deplete the system for the receptors. Now, when we try to actually compute the steady state solutions using the numerical integration of this large ordinary differential equation system, then the problem which happened is that as you will see afterwards, the parameters are varying in their orders of magnitudes from 10 to the power minus 4 to 1 per second. And that leads to a strictly stiff ordinary differential equation, and reaching the steady state solution even were taking minutes of computations. But we actually developed the recurrent structure, which is a novel structure for this chain of compartments, where we can quickly, within seconds, compute the steady state solutions, where if we just need the steady concentration of the receptors at the boundary condition and the parameters, and we can backtrace within seconds the density of the receptors in each compartment. And this recurrent structure actually helped us to examine thousands and thousands of parameters to see how the parameter combinations are actually affecting the distribution of the synaptic Ampa receptors in the spines. Now, here I have given the explicit expressions of the steady state solutions, although I won't go into the details, but this is there in the slides, which is available in the Dropbox. So if one is interested in understanding how is this recurrent structure working, then one can have a look at it. Now, here I am now very soon going to dive into the result section. So the geometrical and reaction parameters, which I'm using here for the results, I would like to mention where the dendritic shaft, the dotted dendritic branch is of a diameter of 1 micron meter, and the length is 100 micron meter. And the small compartments which I have created in that is of the length of 0.1 micron meter. And the neck of all the spines are identical, with of diameter 0.4 micron meter and length 0.5 micron meter. Area of the ESM and the PST is also identical for all the spines, and area of the ESM is 1 micron meter and PST is 1/10 membrane area, and the interspine distance is 1 micron meter. The diffusion coefficient I have already mentioned, and the steady density of the Ampa receptors at the boundary condition, which I'm considering, is 10 per unit micrometer square area. The PST95 binding and unbinding rates are 10 to the power minus 4 per second and 10 to the power minus 5 per second. And the PST95 density available for the Ampa receptor binding in the PST is 150 unit per unit micrometer square. So in the area of 0.1 micrometer square of the PST, we have 15 PST95 SWAT proteins to bind. And these parameters are more or less inspired from the mean empirical estimates available in the experimental literature. So now in part A, what I'm going to show you is how the parameters anterograde, retrograde, endocytosis, and exocytosis, the 4 crucial parameters of Ampa receptor trafficking, may affect the distribution of synaptic Ampa receptors across spines. So we begin with a situation of free diffusion in the PST. So we are, for the time being, ignoring that there is a hinder diffusion of Ampa receptors in the PST, so that when we want that when we apply that, we can see what change does it make. So we start with the free diffusion condition, where we take the dendritic branch and we look at the count of the total count of the synaptic Ampa receptors and the PST95 bound count of the Ampa receptors in the first spine. So what we do is that we take 5 different orders of magnitudes of the endocytosis and exocytosis parameters and combine them into this form, and then we try it for 5 different orders of the anterograde and retrograde parameters. So the orders are 10 to the power minus 4 per second, 10 to the power minus 3, 10 to the power minus 2, 10 to the power minus 1, and 0. So I have shown here in terms of the log of the values. Now, the heat map is actually showing you the count of the total synaptic Ampa receptors in the PST, and here the PST95 bound count. And what we observe is that most of the parameter combinations are actually leading to the saturation of the PST95 slot proteins, and there are only few of them which are actually leading to unsaturated or partially saturated PST95 binding. As well as we also see in the total count that the total count is close to the, for most of the parameters, close to the count of the PST95 bound count, which is maximum up to 15. So as many available slot proteins are there, and the range in the total count in this color zone is 1 to 20. So the thing is that the free receptor counts are very less in comparison to the bound count, and most of the composition of the total count is being constituted by the PST95 bound count. Now, I would like to show you the profile of variation of how the total PST uh, uh, receptor count and the bound PST receptor count actually varies for this combination of the parameters. So we chose this way because this is the best way we could see to actually express the result for 4 parameters. Otherwise, it would have been very difficult to capture this picture for a 4-dimensional uh, profile. So we see that for these parameter combinations, we observe that there is a decrease in the profile, but also for another parameter combinations, we have an increase in the profile. So since in this parameter combination, the PST95 bound count is already saturated, so you see a very fractional change. But the real change which is happening in the total PST receptor count is because of the change in the free receptors diffusing in the Ampa receptors. Now, to capture such profiles for almost all the parameter combinations, we devised a technique that we compute the percentage change in the in the total count of the receptors in the last spine with respect to the first spine. Now, the percentage change actually helps to to inform on the how fast. So if we would have taken the absolute change, we could not have understood how fast the decrease or increase is happening, because that depends on what is the baseline value on the first spine. But taking the percentage change actually removes that effect and helps us to understand how fast it is changing. And we observed that for some combination, the total count is not varying much. For some combinations, it's varying more than 100%. And for some combinations, we observed that the total count decreases by 100%, like goes to 0 value to the last spine. And for the PST95 bound, we observe bound count, we also observe the same, but we only see the decrease because one can't increase the count of the PST95 bound count more than the available slot proteins. So that restricts the distribution of the bound count across the dendritic branch. Now, when we apply the reduced diffusion in the PST, the trapping PST, we observed a very different scenario where the free counts also increased significantly in the spine, as well as more and more parameter combinations. If you see, many of the parameter combinations which were leading to partially saturated PST95 bound count have now become fully saturated, and the variation in the PST95 bound count has also gone low for many of the more parameter combinations. Now, because of the change in the free receptor, the change in the percentage change across the dendritic branch in the total count looks a bit more complex. But we did it for many more combinations. Here I'm showing you only for two situations. And what we conclude is that the ratio of the anterograde supply to the retrograde supply actually sets the baseline of the receptor count in the first spine, and then also decides what will be the direction of the change and how much will be the change, how fast will be the change. So higher is the anterograde supply to the retrograde, higher is the first spine count, and the profile will increase with faster rate. Now, given the baseline set by the anterograde and retrograde, we observed that the relative strength of exocytosis to endocytosis performs a fine tuning where higher is the ratio, higher is the spine count, and faster is the change in the profile set by the anterograde and retrograde combinations. Now, as I showed that the PSD95 for most of the combinations are actually crucially shaping the receptor count, and most parameter combinations exhibit fully saturated bound receptor pool. And trapping PSD significantly increases the free receptor pool and reduces the variation in the bound receptor pool down the branch. We have also studied one effect that is empirically observed in the dendrites, that the parameters of the trafficking mechanisms in the dendrites have been observed to be an order less than the parameters or in the spine head. And when we tried it, we observed that it even further reduces the variation in synaptic receptor count. So this factor actually stabilizes the count of the synaptic receptors across 100 micron meter dendritic branch. But we don't know if we make it like 200 micron meter dendritic branch, how will it be affected? But that's the estimate we have taken up. And then it also explains these profiles also explain why the spine sizes in some dendritic branches, if you see, as you go distally, then the spine sizes increases, and in some branches it decreases, and that has always been mysterious why. But using these homogeneous parameter combinations, we have observed that maybe this is a homeostatic mechanism to accommodate, to compensate for the loss or gain of the receptors across the dendritic branch given different combinations. So with this, I will now jump on to the part B, where I would like to show you how the heterosynaptic effects during LTP and LTD may depend on these parameter combinations. So here, when I am applying LTD in my model.
Gupta, let me remind you that you have about 5 more minutes.
Yeah, I'm looking at the time.
Thank you.
So there's a version 1 where I'm just uh, uh, keeping the spine head size unaffected, but version 2 where I am shrinking it, and in the LTP where I keep the spine head unaffected for version 1, only increasing the PSD95 density, but in version 2 I am enlarging the spine head and decreasing and keeping the PSD95 density unaffected. Now, what we observe that in the trapping PSD situation, the LTD version 2 has more strong heterosynaptic effects than LTD version 1. In the case of bound counts, in the case of bound counts, we don't see much heterosynaptic effects because the PSD95 bound receptors are already saturated to their maximum binding slot proteins. And similarly, we observe in the case of trapping PSD that the LTP version 2, where the spine head enlarges, that in that case we have a stronger heterosynaptic effect. Now, if we remove the trapping PSD situation, we observe that the well-performing LTD version 2, where the spine head was shrunk, and the LTP version 2, where the spine head was enlarged, have now lost their performance, and the heterosynaptic effects have gone down. So with this, I would like to conclude the part 2, where we observe that the set of trafficking parameter combination, which leads to similar synaptic receptor distribution across the branch, does not necessarily mean that they will also exhibit similar strength of heterosynaptic plasticity. And we observe that empirically observed the shrinkage of a spine head during LTD and enlargement during LTP are potentially more effective in heterosynaptic effect than only changes than mere changes in the PST95 density. And the heterosynaptic effects also are observed to happen with a delay. So at the point when I am doing perturbation in the middlemost spine on the dendritic branch, the neighboring spines are getting this perturbation effect with a certain delay. And the significant changes in the free receptor count is only staying for a limited window. So maybe this limited window has an implication that might be used for establishing a correlation between the LTP and LTD events amongst neighboring spines. And the length of the dendritic branch has been seen to affect a lot the amplitude and time kinetics of the heterosynaptic effects. So with this, I would like to conclude this presentation, and I would like to thank the Leverhulme Trust for the independent research funding that they are providing, and the University of Bristol for the excellent research facility and workspace. I would also like to thank my research supervisor, Keanu O'Donnell, for time-to-time suggestions, and my colleagues, members of the Computational Neuroscience Unit, and my lab members for their critical suggestions. So thank you so much for the patient listening.
Oh, thank you very much. You kept your time, Rahul. We have time maybe for a couple questions, maybe one or two, if there are questions on the chat. It's a bit unclear to me what kind of mathematical techniques you're using. I mean, I saw a bunch of ordinary differential equations. Any other techniques that you are using?
Yeah, so for like in this case, like here, the ODEs, so my model is mainly based on ODEs. We are not using partial differential equations. Most of the part, it is linear ODEs, but we are introducing more and more non-linearities in the ODE section. And then we are also involving stochastic differential equation formalism, where we are converting those ODEs into stochastic formalism. And we are also looking at the statistical properties of the receptor distribution.
Okay, so in the SDE case, what kind of noise are you working with? Standard Brownians?
So I'm right now trying to use, we are working on the additive noise as well as multiplicative noise. And in the noise section, we are right now trying to use the Gaussian noise process. So.
And they are motivated by experimental measurements?
Yes.
Okay. All right. I don't see any more questions on the chat. So I think, well, thank you again, Rahul. Apologies for this.
Thanks, Olivia. Thanks.
And thank you for this very interesting talk. And thank you to all speakers who attended this session. We are now going to another session. I see Willem Stana's face on a different topic, which is the future of ICMNS.
Yeah, thank you.